Good morning, everybody. Today we are going to discuss about Ethernet coding possibilities. Generally, you are familiar with how to transfer 1 bit, 0 bit in cable by using voltage values. So, in binary encoding, 1 is coded with high value, 0 will be coded with low value. That is the reason all these zeros are coded with low value. 1 is coded with high value, this 0 is coded with low value, and these all ones are coded with high value. We are all familiar with this type of encoding. Now, what is Manchester encoding? So, here the 1 bit is coded with high-low pair. So, here if you see, this is high, this is low pair representing 1, whereas low and high pair representing 0. Now next second another 0 also represented by same way, that is low high, low high, low high. But once again here 1 is there, that is the reason we are representing high and low. So this type of coding if you do, we say Manchester encoding. Now coming to the differential Manchester encoding, here we begin as usual. 1 is here coded with like high low pair, but here instead of talking about 1 as it is, here basically transition here nothing but in the last stage we are at low level and we are moving to high level. This transition here indicates the coming value is 0. Now see the next value also here, present we are here and we are taking transition, so next bit is 0. Next, take the next one, here also we are at low level, we are moving to high value, transition exists, so it represents 0 like this. But once you come to this position, here lack of transition is involved, so there is no transition indicates this bit is 1. So in Manchester encoding, 1 is represented by high-low, 0 is represented by low-high. Whereas differential Manchester encoding, whether transition exists or lack of transition, so these two are used to code either 0 or 1. So Manchester code encoding and differential Manchester encoding are popular. Why? Because binary encoding is high, that is the 1 representation, low for 0 representation, but here it is not that case. When compared Manchester encoding and differential Manchester encoding, noise point of view, differential Manchester encoding is giving better results. So this is the discussion on coding. So in the next discussion, we are going to discuss about frame formats. Basically, already in the last lecture, we have seen various details of Ethernet and cabling possibilities. There I mentioned when you see Ethernet and 802.3, that is actually framed by IEEE. Most of the time we consider both are same, but there is a minor difference if you observe here. The first frame format is DICS Ethernet, second frame format is IEEE 802.3. Basically, why do you need a frame format? our interest here in LAN, we want to carry data from one place to other place. So if you see in both frame formats, data item is available. So actual information which we are interested to transfer from one place to other place, there within the data field we keep that information. Properly transmit the data, we need other helping bits also. So these are all called, we say, headers. Already this we have discussed in the unit 1. So now we are going to discuss about why you are taking other possibilities. So first we discuss DIX Ethernet, and then we'll discuss IEEE 802.3. So what is the major difference between these two? When you see the DIX Ethernet preamble, we are using 8 bytes, whereas in IEEE 802.3 preamble 7 bytes and startup frame delimiter we are allotting 1 byte. But anyway you want to transfer information, we need two addresses. One is source address and destination address. That is common in both the cases. But in DIX Ethernet, here 2 bytes meant for type, whereas IEEE 802.3 it is meant for length. Anyway, pad is needed, checksum is needed. Already we have computed checksum. All of you know the how to calculate checksum also. Here 4 bytes meant for checksum. 4 bytes means almost 32-bit checksum, this one. So how do you work out? Basically, even though here we call checksum, but in checksum here we are using in a general sense. This we'll discuss in the coming slides. What is the here checksum, and now what is pad? So this pad varies from 0 to 46 bytes. Why you need this pad? Suppose data is very low value. When data is very low value, we are working in LAN. Suppose you take one node available in EC block and another node available in main block of Vasavi College of Engineering. So these are the two nodes. If you see, one is situated in one corner and another one is situated in another corner. We are interested to transfer data from one node to last node. You have to maintain a minimum size of the frame. Suppose data is very low value, then you cannot meet the minimum size of the frame. That is the reason we are adding the pad. That is the reason pad varies from 0 to 46 bytes. Suppose data itself, we have high data, that is nothing but suppose maximum data 1500 bytes is available, then no need of adding pad. Suppose it is very low value, then you have to add pad 46 bytes so that your first bit of the frame can reach the last node in the LAN. So that is the minimum condition to be satisfied. That is the reason we are adding pad. Otherwise, what will happen? Suppose at a particular one computer you take, if I release frame in ECE block, suppose frame size is very less. Suppose by the time it reaches CSC, my last bit is already delivered. Then what I conclude? I conclude that my frame transmission is successful. But when the frame is going to the Vasavi College main block, So meanwhile from CSC to library, it is traveling via library. At a library, someone can enter and someone can give data, then automatically collision will happen. So how do you know whether your frame is successful or not? That is the reason you have to wait till first bit reach the last node in the LAN. So that is the reason we keep some minimum length of the frame. That is the reason we add pad value 0 to 46 bytes. If data is very high, no need of adding pad. Suppose data is low, you have to add the pad. So that is the importance of pad. Now coming to the elaborations, even though earlier we have mentioned checksum here, but in frame Ethernet frame formats, we are not using checksum. We are using CRC. This one. This checksum used as a in a general sense, but examination point of view, don't write this is a checksum. You have to write as CRC. That is nothing but in Ethernet or IEEE 802.3, we are using CRC. That is nothing but cyclic redundancy check. How many bits that one? That is a 32 bits. CRC 32 bit we are using. This is the CRC. In Ethernet we are using CRC. So why do you need preamble? Suppose 8 bytes is used in the case of first one, that is Ethernet case 8 bytes, whereas IEEE 802.3 we are using 7 bytes preamble. Basically, if you see the preamble 8 bytes pattern, so one byte containing 10101010. This is nothing but high low value, nothing but a clock. This is nothing but a clock. So this is to synchronize the receiver. We use this type of clock. In IEEE 802.3 also we use the 8 bytes, but 7 bytes we use this clock, but 8th byte is 10101011. This is 11. That is the only one difference. Whereas in the case of Ethernet, we are using this is also 0, but whereas IEEE 802.3 here we are using 1 to discriminate the preamble, and we are going to start the other things. That is the reason this is start of frame delimiter 1 byte is added by IEEE 802.3. Coming to destination address, source address, you are familiar. This is nothing but physical address or MAC address. We say 6 bytes means total 48 bits. This one. Now coming to length or type, in Ethernet case we say that is the type, whereas IEEE 802.3 case we say length. So what is this type basically? When you are carrying the data related to the IP, that is one of the types, or you are carrying the data related to novel network, or whether you are carrying the data related to the AppleTalk network. Like this, to discriminate all these things, we use the type in DIX Ethernet. Coming to IEEE 802.3, we use that is the length field. So number of bytes in the data field. When you take data here, how many bytes are there? Why? Because data is variable. It is varying from 0 to 1500 bytes. How do you identify? So that is the reason we are using length in the case of IEEE 802.3. Anyway, we know how to calculate CRC. So basically this is used for error detection. So this is the overall idea of the various fields available in the frame. Basically our frame carries data from one place to other place. To carry this data we need source address, destination address. This is for synchronization. and length indicates what is the data size, present data available, so that we can extract information. And why you need padding? Suppose there is no padding, first bit may not reach the last node. By the time sender may feel that successful transmission. So to avoid that, the minimum frame size you have to maintain in such a way that your first bit should reach the last node. So till that time, sender has to transmit bits. So that is the reason we are adding padding. Anyway, CRC is used for error detection. So we are sending in this way. So at the receiving end, first we receive these bits. So this is nothing but clock synchronization purpose. After that, we can deliver this frame to the particular destination address. We can identify from which source it is coming and how many bits you have to take from this field so that we can extract the information. Coming to the Ethernet address, this is nothing but physical address or MAC address. We know this is 6 bytes, 48 bits. Flat address, it is not hierarchical. This is bound into the network interface called ROM, and one 48-bit address if you see, basically this is a hexadecimal. So each one is represented by 4 bits. So 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 12 into 4, 48-bit address. This is the Ethernet address. So for better understanding, you may refer all these books, Computer Networks by Tannenbaum, or Data Communication Network by Ferojan, or TCP by Protocol Suite Ferojan, or you can find lot of literature in internet related to this frame formats. Thank you for your attention.